Okay, moving on to a little bit more of a tricky problem. I actually encourage you to try this one yourself. Pause the video here, try it yourself, and then when you get stuck, you can unpause and follow along. All right, here we go. First of all, we're asked to calculate the total resistance of this circuit. And we know for resistors in parallel, which there's 3 resistors in parallel, the equation for the total resistance is going to be 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, right? It actually tells us here in the question that all the resistors are 25 ohms. So let me actually just label that right now. 25, 25, and 25, okay? So if we just plug those 3 things into this, we would get something like this. 1 over the total resistance equals 1 over 25 plus 1 over 25 plus 1 over 25. Of course, there's ohms on all of those, but that's okay. We know that that's the case. So if I plug this in my calculator, 1 over 25 plus 1 over 25 plus 1 over 25, it gives me 0.12. And then remember, that's what 1 over RT equals. So in order to find what RT equals, we just need to do 1 over that, 1 over 0.12, to flip the fraction. So RT, oops, where's my pen? There's my pen. RT is going to equal 1 over 0.12, which is just 8.33 ohms, which agrees with our answer there, right? So that's just running to 3 significant digits. Those 3's actually just keep repeating forever, but this is okay. So now, essentially what we've done, always remember this, what we've done basically is we've turned this complicated looking circuit, we've replaced these 3 circuits, we sort of combined them and replaced them with a single resistor that has a value of 8.33 ohms, right? And if it's a simple circuit like this, we can easily determine the current, right? Because we can just use Ohm's law. We know that current equals V over R, or voltage over our resistance, right? Our voltage is 6 volts. The battery tells us it's 6 volts, right, in that diagram. So it's 6 volts over 8.33 ohms, which gives us a total current, a current coming out of the battery of 6 divided by 8.33 gives us 0.72, about 0.72 amps, if we round to 2 significant figures. So there we go. That's the current. If I zoom in here, that's the current that's going here, 0.72 amps, and also the current that's coming back to the battery, right, is 0.72 amps, assuming no electrons are lost along the way, right? Now, we know that 0.72 is going to get split 3 ways, basically. Some of it's going to go to each one of those resistors, and that's going to be the next goal, to figure out how to split it up. And it's actually very similar to question 2, which we did above, how to determine how much goes to each resistor. We can just use, again, we use Ohm's law. So like, for example, if we take resistor 1, we can look at resistor 1 and remember what we know. We know that the voltage across that resistor is just going to be 6 volts because there's nothing in between the battery and this resistor, right? There's a straight path between those 2 things, so on either side. So basically what that's telling us is the voltage drop here is 6, 6, and 6, right, across all those. So if that's the case, we know our voltage, we know our resistance, so we can just use Ohm's law again. The same version of Ohm's law that we used for part B, right? I equals V over R, where the voltage is 6 volts, and the resistance is the resistance of R1, which is 25 ohms. And if we do this, 6 divided by 25, it's going to be 0.24 amps. So that's resistor 1. You could repeat the same thing for resistor 2 and resistor 3, but notice how all of them have the same resistance. So if they have the same resistance and they're the same voltage, we're going to get the same answer for all 3. And think about this. If we have 0.24 amps here, so let's actually label this on our diagram. If we have 0.24 amps here, 0.24 amps here, put amps, 0.24 amps here, Does that make sense with the fact that the total current is 0.72? Well, let's think about it. If we add these up, do we get 0.72? I'm going to try it right now. 0.24 times 3 basically, right? That gives me exactly 0.72. So it makes sense. And it makes sense that essentially when you have all the same resistances in our resistors, that essentially the current is split 3 ways equally. So if you realize that all the resistors in parallel have the same resistance, you can just take your total current and divide it by 3. Because the same amount of electrons are going to go through each of these resistors. Because there's not one that's easier to get through than others, right? They're all the same difficulty to get through because they all have the same resistance value. So there we go. That's our answer to that question. All right, moving on to question 4. Now, this one is a little bit different because, well, look at it. We have these 2 resistors here, which are just in line, and then we have these 2 resistors here, which are in parallel. So it's like these 2 are in series, and then these 2 are in parallel. So we've got multiple things happening here. It makes it a little bit more complicated. We know how to deal with if they're just in series. We just add up the resistances, right? But we can't do that here. We can't just add these up because these 2 are in parallel. We need to first, essentially what we need to do is we need to look at this piece here. We need to take these parallel resistors and find the total resistance of that resistor, or those 2 resistors. Because if we do that, we can represent them as one resistor, right? So we're basically breaking this down, simplifying it to make it easier for us. So if we just look at resistor 2 and 3, so this is the way I'm going to do it. I'm actually going to do it over here right underneath. I'm going to say the resistance of 2 and 3 is what we're looking for right now. So remember, in parallel, our equation looks something like this. Let me get my pen. 1 over the resistance of 2 and 3, that's how I'm going to do it. I'm going to do 2 and 3 like that, is equal to 1 over the resistance of 2 plus 1 over the resistance of 3, right? That's our equation. So combining those is going to be 1 over 30 ohms plus 1 over 50 ohms. And if we do that in our calculator, 1 over 30 plus 1 over 50 is going to give us a number. It's 0.05333 repeating, blah, blah, blah. But in order to find out what our resistance of 2,3 is, we need to do 1 divided by that, right? Because we need to flip the fraction. So resistance 2,3, if we flip it, 1 divided by that gives us exactly 18.75. Again, it makes sense that it's lower than these 2 resistances because it will be easier for electrons to go through both of them because it splits the current. So essentially what this tells us is it tells us we can represent these 2 resistors as one resistor with this resistance, 18.75. So essentially what I'm going to do, I'm going to redraw that circuit like this. So we have a resistor here, that doesn't go away. But then those 2 resistors, I'm just going to replace with 1 resistor here, and then there's the 3rd resistor here. So this is resistor 2,3, because it was combining 2 and 3. This is resistor 4, and this is resistor 1, right? And now we know all the resistances of these. This resistor 4 was 20 ohms, stays the same. 2,3 we calculated as 18.75 ohms, and resistance 1 is 20 ohms. Now can we find the total resistance of the circuit? Yeah, because we know when you have resistors in series like this, we can just add up those resistances, right? So the total resistance of the circuit, RT, is just going to be 20 plus 20, the top and the bottom one, plus 18.75, right? Which, when we round that to 3 significant figures, it's going to give us the answer exactly that's on top, 58.8 ohms for the entire circuit. So essentially, again, we've even more simplified this circuit. We've said if we took all those resistors and combined them into one, we would get a circuit that looks like this. One resistor that has an equivalent resistance of what was the number 58.8 ohms. So it's like we've taken this complicated circuit, and first of all, we made it simpler by combining the parallel part. And then what we did is we just combined those three in series to give us one resistor. So this diagram right here basically represents this whole thing, right? So in order to calculate the total current coming out of the power supply, all we got to do again is use Ohm's law, I equals V over R, right? Because current equals the voltage over the resistance. The voltage of the battery, or the power source, it is a battery here because it looks like that on the diagram, is 10 volts over, what was it, 58.8 ohms. And if we do that, 10 divided by 58.8, that gives us 0.17, which agrees with our answer up there. There we go. So that is 0.17 amps is our current basically going through the whole thing. So back to our diagram here, our first diagram, that means here, coming out of the battery, our current is 0.17 amps, and coming back through the battery here, or on this side, is also going to be 0.17 amps. Now we know that's going to be split, right, here and here. We're going to split up that current, and we're going to split up that current, but we know going through this resistor here, resistor 4 and resistor 1, it's going to be that 0.17 amps because no electrons are lost in between there. They just split up here and come back together here. So the next question, this is where you just have to keep track of what you're doing. The next question asks us to find the voltage and current through each resistor. So basically how much voltage is lost through each resistor and how much current is going through each resistor, right? So let's just make a little table for ourselves here. What we want to do is we want to find the voltage. So we have 4 resistors, right? R1, R2, R3, and R4. And what we want to find is we want to find the voltage through each one of those, and we want to find the current through each one of those. So here's our table. And it'd be good if you set up a little table like that as well. It just keeps, it makes keeping track of our answers a little bit easier, right? Let's start off by filling out what we already know. So we know, for example, what's going to be the current through resistor 4? Well, didn't we say it's going to be this whole 1.17 amps? It doesn't split up or anything, right? So we're going to get that 0.17 amps through resistor 4. So 0.17 amps. No big deal, right? Same thing through resistor 1, 0.17 amps. So we can just put that in, 0.17 amps. We know that right away. Can we, if we know the current there, right, can we find the voltage drop across that? Well, remember voltage, if we look at Ohm's law, voltage is going to be voltage is going to be I over R, right? No, sorry, I times R, my bad, right? If we rearrange this equation here for voltage, it's like we're multiplying I and R. So just in this actual table, I'm going to write V equals IR, right? So all we need to do to find the voltage drop through this resistor is to multiply the I by the R. And we know the resistance, right? It's given in the question. We can actually put that here in our table as well. So resistor 1 and resistor 4 both have a resistance of 20 ohms. So I'm actually just going to put that here, 20 ohms and 20 ohms. So all we have to do to find this value is multiply our current by our resistance. So 20 times 0.17. 20 times 0.17 is 3.4. So the answer here is 3.4 volts. It's going to be the same thing down here because 20 times 0.17 is also 3.4 volts, is also lost across that resistor. There we go. So that's okay. The next part is where it gets a little bit more tricky, so we just have to be very careful here. Resistor 2 and resistor 3. So resistor 2 has 30 ohms of resistance. I'm actually just going to record that in the table. And resistor 3 has 50 ohms. So this is going to be 30 ohms. ohms, just so we can keep track of that, right? Now, how can we figure out the voltage drop and the current through each one of these resistors? We know it's going to split up, but it's not going to split up evenly because the resistances are different, right? But what we can do is we know the resistance between 2 and 3, right? If we combine these resistances here, we should get 18.75. So what we can figure out is we can figure out this voltage drop because we know the current through both of these combined is going to be the same current as is through the rest of the circuit, 0.17 amps, right? So here we're sort of looking at this diagram at 2 and 3 combined. The current through both of those together is going to be 0.17 amps. So I'm just going to show here that the current combined here is 0.17 amps. That doesn't necessarily mean it's going to be split 50-50, but the total is 0.17. So if that's the case, we can just find the voltage in the same way, the voltage drop, in the same way that we found it for the other ones. We just multiplied I by the R. And in this case, the R is the combined resistance of these two, which we already calculated as 18.75. So if we do 18.75 times 0.17, 18.75 times 0.17, that gives us 3.19. 3.19 volts and 3.19 volts. Judging by our previous examples, you should understand why the voltage is the same for resistors in parallel, right? Because there's basically the only thing connecting them is a wire, and wires don't have any resistance. So that the voltage drop has got to be the same for both of them. So this is the most difficult part of it, and this only happens when you have parts in series. You always have to look at the combined value to figure out what the voltage drop is going to be across those. Now, once we're this far, the rest is pretty easy because we know the current, if we want to calculate the current now, current is just V over R, right? Oops, let's do that in blue, sorry. I equals V over R. So if we know the voltage and the resistance for resistor 2, 3.19 and 30, we can just divide 3.19 divided by 30 to find out the current there. 3.19 divided by 30 is 0.11 approximately. So this answer here is 0.11 amps. And if we do the same thing for resistor 3, we do 3.19 divided by 50, 3.19 divided by 50, we get 0.06 amps. Oops. 0.06 amps. There we go. So basically what this says is 0.06 amps goes through this resistor 3, and more than that, about twice that amount, goes through resistor 2. And that makes sense because resistor 3, it's harder for the electrons to go through because it has more resistance. Also, another thing to check is these two currents, when we add them up, equal the total the total current of those two resistors, the amount that goes through both of those resistors here. So that's true. It makes sense, right? And the last thing to check is on our diagram, right? So let's go back to our diagram here. I'm going to zoom in. We said 0.11 amps goes through this resistor, and 0.06 amps goes through this resistor. Does this make sense with how much goes through the whole circuit, this 0.17? It does, right? Because we have 0.17 here, right? And if we add up 0.11 and 0.06, it's going to give us 0.17. So we're actually okay because these two add up to this. And same thing here, when these two come back together, they're going to add back up to 0.17, right? 0.11 plus 0.06 equals 0.17. So we're okay. We found our answer. So once again, just to sort of go over this whole question, because it can look long and overwhelming, it's a little bit of a tricky question. The first thing we got to do is break up the circuit, or break it down into a simpler circuit by taking any resistors in parallel and representing them as one resistor, right? Once we've done that, we can easily add up the resistances to find the total resistance of the circuit. Once we have that, we can easily find the current through the entire circuit. And then there comes this part where we have to break down the voltage and the current of each part in the circuit. Now, when we do this, we usually start with the voltage and then work towards the current, but it depends on the case. We'll do more questions in class, but go over this and go over it more than once if we need to try to understand what's going on here. I want you to give this last problem, actually problem 5, not the last problem, problem 5, I want you to give this one a shot yourself. See if you can answer these questions, follow the same pattern we did in the previous question, and see if you can figure it out. Question 6, the one below it, that is a challenge problem. That's more difficult than you'll see on any test or exam in this course. So this is a challenge problem. So this is only if you're really good, if you really understand all the previous problems and you want a little bit of a challenge. All right? There we go. So finish off problem 5, try yourself, come to me in class with any questions you might have about it.